So picture a syringe.
Okay.
It's filled with this perfectly clear liquid. And a clinician is standing there, right, about to inject it directly into your knee to treat, say, osteoarthritis. Or maybe they're injecting it into the delicate tissues of your face for, regenerative aesthetic.
Right, a very common scenario these days.
Exactly. And as the patient in that chair, you probably look at that clear liquid and just think of it as a finished, perfect product, like a simple chemical equation that's clean, precise, and just ready to heal you.
Oh, absolutely. I mean, it's completely natural to view it that way. We're all conditioned to see medicine as this very binary thing.
Right.
Like it's either medicine or it isn't.
Right.
But the moment you step into the world of biological manufacturing, specifically treatments that are extracted from natural sources, that clear liquid becomes, well, a wildly complex biological landscape.
Yeah, it's not just water and salt.
Not at all.
Yeah.
It's teeming with microscopic variables and, frankly, potential impurities.
And that is exactly why we're doing this deep dive today. We're going to pull back the curtain on the invisible, but just incredibly rigorous rule book that keeps that clear liquid from, putting you in the hospital.
It's a very necessary rule book, too.
For sure. Our stack of sources today is fascinating. We've got pharmaceutical patents, FDA guidelines, highly detailed manufacturing documents, and most importantly, the specific compendial monographs from the United States Pharmacopoeia, the USP, and the European Pharmacopoeia, the EP.
Yeah, and for those who might not know, those pharmacopoeias are essentially the ultimate law of the land for medical manufacturing.
The big bosses.
Exactly. They dictate the exact boundaries for extraction, purity, and sterility verification for biological compounds. If a manufacturer wants to call their product medical grade, they have to survive the gauntlet laid out in these documents.
Which brings us to the actual material we're talking about today. Medical-grade polynucleotides, commonly known as PDRN. These are basically DNA fragments that are being injected into human bodies to trigger this miraculous cell repair and regeneration. But here's the kicker you might not know. A massive portion of this PDRN is derived directly from the reproductive organs, specifically the sperm or testes of salmon.
Which sounds completely wild when you first hear it.
It sounds insane, like actual fish sperm.
It does, but from a strictly biological standpoint, fish sperm is just incredibly dense with high-quality DNA. It is the ultimate raw material for these regenerative therapies.
Okay, but obviously you can't just grind up a salmon, filter it through a coffee sieve, put it in a syringe, and inject it into someone's face.
Please don't do that.
Do not try this at home. The difference between a miraculous healing process and a severe immune reaction comes entirely down to the microscopic extraction standards we're about to explore.
Yes, the extraction is everything.
So let's get into the anatomy of that extraction. How do we actually get from raw salmon material to medical-grade PDRN?
Well, to understand the how, we first have to agree on the what. So PDRN stands for polydeoxyribonucleotide.
Polydeoxyribonucleotide. Got it.
It's a mouthful. But our sources describe these as polymers formed by nucleotide chains. Simply put, they are fragments of DNA made up of nitrogenous bases, sugars, and phosphate groups.
Okay, the basic building blocks of life.
Exactly. But when you start with a raw biological source like a fish, that DNA is wrapped up in an incredibly messy package of proteins, lipids, and just other cellular components that you absolutely do not want in your final product.
Right, because the human body's immune system would view those extra fish proteins as a hostile invader.
Right, 100%. It would attack them immediately.
So the patents outline this incredibly aggressive multi-step purification process. And it starts with an enzyme lysis of the protein organic matrix.
Yeah, and think of those enzymes as microscopic chemical scissors.
Chemical scissors. I like that.
They're introduced into the raw material specifically to chew up and break down all the unwanted proteins that are just tightly bound to the DNA. Once those proteins are sheared away, the manufacturers run a clarifying filtration.
To physically separate the bulk of that broken down organic junk from the solution, right?
Exactly. Just filter out the trash.
But they're not done there. Next comes precipitation using quaternary ammonium salts.
This is a crucial chemical step. By introducing these specific salts, they alter the solubility of the molecules in the liquid.
Wait, what does that mean exactly?
It means the nucleic acids essentially crash out of the solution. They clump together so they can be easily separated from the rest of the liquid.
Oh, wow, okay.
But now you have DNA tangled up with the salts, so you have to run a decomplexing step to basically wash those salts away.
Okay, let's unpack this because the next step the patents mention is molecular selection using column chromatography.
Yes.
Now, I feel like the word chromatography gets thrown around a lot in chemistry, but here it's doing some serious heavy lifting. I want to try to visualize this. It's not just like a coffee filter, is it? It's more like a microscopic plinko board or like a maze of porous beads.
That is actually a brilliant way to picture it. In column chromatography, you have a physical tube packed with a stationary phase, usually these tiny, highly porous resin beads.
Okay.
And you pump your decomplexed DNA solution through this tube.
And as it flows through, the smaller molecules actually wander into the microscopic pores of the beads, right? So they get stuck and delayed in the maze.
Precisely. Meanwhile, the larger, bulkier molecules just bypass those pores completely and wash straight out the bottom first.
That is so counterintuitive. The big stuff falls through fastest.
It is, but it separates the molecules perfectly based on their exact size and weight. And that's where the manufacturer isolates the specific polymer lengths they need.
Which brings up what is probably the single most critical parameter in this entire extraction process, right? The molecular weight of the PDRN.
Without a doubt.
Because the sources state that effective PDRN fractions have to fall within 50 to 1,500 kilodaltons.
Yes, and what's fascinating here is that the molecular weight literally dictates whether this substance will act as a powerful regenerative medicine or just sit there as expensive, useless water.
Wow.
The manufacturing process has to thread a microscopic needle. If the DNA is sheared too aggressively during that harsh enzyme lysis we talked about, or if it's exposed to uninhibited nucleases.
Wait, what are nucleases?
They're stray enzymes that just chop DNA into tiny pieces. If that happens, you lose the required polymer length.
So I want to push back on this for a second. If the goal is to get this DNA into the tissue to work its magic, why is there a floor and a ceiling?
What do you mean?
Like, why not just use the longest, most intact DNA chains possible? If bigger is better, why cap it at 1,500 kilodaltons?
Oh, it's a great question. And it really comes down to fluid dynamics and cellular biology. If the chains are too long, like if you go way over that 1,500 kilodalton ceiling, the resulting solution becomes incredibly viscous.
Like syrup.
Worse, it turns into a thick, unwieldy gel. You wouldn't even be able to push it through a fine-gauge needle for a joint injection.
Ah, okay.
And even if you could, the body's tissues would have a much harder time absorbing and utilizing it. It just sits there.
Makes total sense. But what about the floor? What if the chains are chopped up too small, falling under that 50 kilodaltons mark?
Well, if you lose the length, you lose the biological function. The regenerative magic of PDRN comes entirely from its ability to bind to and activate specific receptors on the surface of human cells.
The adenosine A2A receptors, right?
Exactly. If the DNA chain is chopped up into tiny fragments, it physically cannot span the binding site of those receptors.
So it's kind of like handing someone a fully assembled, precision-cut brass key to unlock a door versus handing them a handful of melted brass shavings.
That is exactly it.
Like, both are technically made of the exact same material, but only one is actually shaped correctly to turn the tumblers and open the door.
That's the perfect analogy. And the industry actually has a term for those useless brass shavings. They call it hydrolyzed DNA.
Hydrolyzed DNA.
Right. It's cheap. It's very easy to manufacture because you don't have to carefully protect that specific polymer length. But it is completely ineffective for tissue regeneration. It just won't bind to the adenosine receptors.
And the sources show that for specific, highly targeted treatments, that wait window gets even tighter.
Oh, much tighter.
Yeah. For a specific intra-articular joint treatment called chondrotide, which is designed for osteoarthritis, the sweet spot is strictly between 70 and 240 kilodaltons.
Which just proves how dialed in that chromatography has to be. I mean, they aren't just grabbing any DNA. They're isolating a highly specific therapeutic fraction.
Well, here's where it gets really interesting.
Yeah.
Because having the correct molecular weight is only half the battle. We now have to transition from physical extraction to analytical proof. You have this vial of perfectly sized DNA fragments. How do these manufacturers actually prove to the regulators that this liquid is pure PDRN and not just contaminated fish soup masquerading as medicine?
Yeah, this is where the compendial standards really drop the hammer.
Right.
We're looking closely at EP 10.00 monograph 04-2020.2710 for polydeoxyribonucleotide and USP Chapter 10L43 for ancillary materials.
And USP 10L43 takes a very strict risk-based approach, right? Like, it's not just about testing the final liquid, it's about proving the entire history of the material.
Entirely. Under USP 1043, you must provide exhaustive documentation of biological traceability. Regulators want to know exactly where that salmon came from.
Like its literal address?
Pretty much. Was it a regulated, disease-free aquaculture facility? You have to prove the absolute absence of external exogenous factors.
Which means what, exactly?
That means demonstrating there are no environmental contaminants, heavy metals, or rogue viruses that hitched a ride from the raw material.
Wow. But the real test is the purity metric itself. To earn the label of ultra-pure lyophilized PDRN, and lyophilized just means it's been freeze-dried into a stable powder, it has to hit a purity threshold of greater than or equal to 95%?
Yes.
But you can't just put microscopic DNA on a tiny scale and weigh the impurities. How are they physically proving that 95% number?
They rely on the physics of light, believe it or not, specifically UV spectrophotometry.
UV light?
Yeah. They take a sample of the PDRN and shine specific wavelengths of ultraviolet light right through it.
Oh, because DNA and proteins absorb light at completely different frequencies?
Yes, and the mechanics of why are just fascinating. The nitrogenous bases in DNA have these aromatic ring structures that aggressively absorb UV light at exactly 260 nanometers.
Okay, 260.
But the peptide bonds and aromatic amino acids found in proteins, the stuff we desperately want to get rid of, they peak their light absorption around 280 nanometers.
So the regulators are looking for a very specific UV identification mark. The maximum absorption of the sample has to hit at 258 nanometers, plus or minus 2.
Exactly. And then they calculate the crucial A260 over A280 ratio.
Which is just division, right?
Right. They divide the absorbance value at 260 by the value at 280. If you have pure nucleic acid, you will score a ratio strictly between 1.8 and 2.0.
And if you don't,
well, if that ratio drops down to, say, 1.5, it means there's a massive spike in light being absorbed at 280 nanometers.
which screams, hey, you have a bunch of raw fish protein hiding in this vial.
Exactly. It fails the test immediately. Throw it out.
And our sources issue a really stark warning here about the so-called gray market. You'll sometimes see cheaper products labeled as partially purified PDRN, boasting maybe 70 to 90% purity.
Yeah, or they'll use a vague cosmetic-sounding marketing term like marine polynucleotides.
Right. And this raises an important question about how we view those remaining percentages. A 90% purity rate sounds like an A grade in high school, but in biological manufacturing, that missing 10% isn't just empty space or harmless water.
No, it's residual host cell proteins. It's the leftovers of the fish. And if you inject 10% foreign fish protein directly into a human joint or under the skin of their face, their immune system is going to go absolute haywire.
It's an allergic nightmare.
It will treat it like a full-blown biological attack.
Yeah.
White blood cells and macrophages will just flood the area. That's exactly how patients end up with severe localized allergic reactions, massive swelling, and chronic granulomas.
Granulomas, that's where the body literally builds a wall of scar tissue around the foreign protein to isolate it, right?
Yes, it's painful and very hard to treat.
So pushing for that greater than 95% purity isn't just about making the product quote-unquote premium or charging more money. It's a fundamental safety requirement.
It is the bare minimum. In fact, if we look at EP 5.2.2, which governs raw materials for cell-based and gene therapy products, the scrutiny over those residual host cell proteins is intense.
A single bad batch with too much residual protein can destroy the safety profile of an entire line of medical devices.
Exactly. That's why the sources detail that the highest tier manufacturers don't just run their product through the chromatography column once, they use triple chromatographic refinement.
Running it through that microscopic maze 3 separate times, just to systematically shave off impurities until they eliminate 99.9% of non-DNA material at the molecular level.
All to ensure that 1.8 to 2.0 UV ratio is absolutely bulletproof.
Okay, so let's pause and assess where we are in this journey. We've taken raw material, used enzymes and salts to isolate the DNA. We've used triple column chromatography to get the perfect 50 to 1500 kilodalton molecular weight so it binds to the adenosine receptors.
Right.
We've used UV light to prove it's over 95% pure, hitting that perfect 1.8 ratio. We've eliminated the fish proteins, so we're done, right? It's totally safe to inject.
Doing that would be catastrophic.
Yeah, because we've completely ignored the most terrifying variable. Purity and sterility are not the same thing.
Not even close. I mean, you can have a 100% pure, perfectly sized strand of salmon DNA. But if there is a single living bacterium floating in that vial alongside it, you have a massive problem.
Which brings us to the ultimate shield in our deep dive today: sterility verification and endotoxin limits. We really have to remember what DNA actually represents at a fundamental biological level. To a bacterium, highly refined, purified DNA is essentially premium, nutrient-dense
So
fertilizer.
it's an all-you-can-eat buffet.
Yeah.
DNA provides the carbon, the nitrogen, and the phosphorus that microbes need to just thrive. If bacteria contaminate a vial of PDRN, they will multiply exponentially.
So how do the USP and EP rulebooks lock this down?
Well, they demand verification under two heavy-hitting chapters: USP 85 for bacterial endotoxins and USP 51 for antimicrobial effectiveness testing.
Okay, let's start with the sterilization process itself. The sources dictate that manufacturers must use terminal sterilization,
Yeah.
which usually means gamma irradiation or high-pressure autoclaving at 120 to 121 degrees Celsius for 15 minutes.
Right. That's essentially using extreme heat and pressure to violently destroy any living organism in the vial.
But wait, what if this specific formulation can't survive that? You mentioned earlier that DNA polymers are fragile. Doesn't blasting them with 121-degree heat run the risk of breaking those delicate nucleotide chains we just worked so hard to preserve?
It absolutely can. That's a huge risk. So if the specific matrix is too heat sensitive, the pharmacopoeias allow for aseptic filtration instead.
Pushing the liquid through microscopic filter membranes that are so tight the DNA can slip through, but bacterial cells get physically trapped.
Yes, but here is the terrifying part about bacteria. Simply killing them or filtering out the live ones isn't actually enough to make the product safe for injection.
Because of endotoxins. This is where the biological mechanics get really wild.
They really do. Endotoxins are lipopolysaccharides, essentially structural components of the outer membrane of certain gram-negative bacteria. So when you use heat or radiation to kill bacteria, their cells burst open, right? Leaving behind these dead cellular shells just floating in the liquid.
And if a doctor injects those dead bacterial shells into your body, your immune system doesn't know they're dead.
Exactly. Your immune system's toll-like receptors immediately detect those lipopolysaccharides and trigger a massive systemic defense response.
A pyrogenic reaction.
Yes.
You get a sudden spiking fever, severe inflammation, and potential tissue damage, all from bacteria that were already dead.
Which is why USP 85 sets exact, incredibly strict allowable limits for these endotoxins, measured in endotoxin units, or EU.
And the testing for this is highly specialized, right? Measuring the biological reactivity of the sample to ensure those dead shells aren't present in dangerous numbers.
Yes. For the raw lyophilized PDRN powder, the limit is less than 1 EU per milligram.
Which is an infinitesimally small amount.
And depending on where the product is actually being injected, the rules tighten even further. For the chondrocyte injectable joint treatment, the limit drops to less than or equal to 70 EU per milliliter.
Wow.
But for highly refined dermal fillers, where the PDRN is being injected right into the highly vascularized, delicate tissues of the face, the limit plunges to a staggering under 0.25 EU per milliliter.
Less than a quarter of a single endotoxin unit per milliliter. Achieving that requires a level of pharmaceutical washing and environmental control that is genuinely hard to comprehend.
It is incredibly difficult to pull off.
But I have another hypothesis for you to challenge. Let's say the manufacturer hits that 0.25 EU limit. The vial is perfectly sterile when it leaves the factory. But the second a clinician pops the seal in a treatment room, the liquid is exposed to the air.
Right.
If DNA is superfood for microbes, how do manufacturers prove the liquid won't just immediately become a petri dish once it's opened?
Well, if we connect this to the bigger picture, that exact scenario is why USP 51 exists. This is the antimicrobial effectiveness testing standard. It's not nearly enough for a manufacturer to say, hey, our factory is perfectly sterile. They actually have to prove the formulation itself can actively defend against contamination after it's opened. To do this, they perform challenge testing.
Meaning they intentionally attack their own finished product?
Literally. They take their pure, sterile PDRN solution and they intentionally inoculate it with horrific pathogens.
Oh, wow.
The sources specify they use aggressive strains like Staphylococcus aureus, Escherichia coli, and the yeast Candida albicans.
They inject E. coli into the medicine.
They do. They do it to prove that the preservative system engineered into the product can actively fight off those microbes, neutralizing them over a specific time period. It proves the liquid has its own active immune defense.
That is wild. And the sources are very clear on a detail that anyone working with these products needs to understand. Simply slapping the word purified or saline solution on a label absolutely does not mean it is sterile or safe for injection.
Far from it. Furthermore, the pharmacopoeias dictate that manufacturers have to choose the appropriate preservatives.
Right. For instance, using a common preservative like EDTA might be perfectly fine for an over-the-counter contact lens solution, but it is entirely inappropriate and potentially damaging to inject into open skin channels during a microneedling procedure or a dermal injection.
So what does this all mean? We've traced an incredible biological journey today. We started with the raw reproductive material of a salmon.
A very weird start.
Very weird. We walked through aggressive enzymatic lysis, quaternary ammonium salt precipitation, and the microscopic maze of triple-column chromatography. We used UV spectrophotometry to prove a 95% purity rate at a 1.8 light absorbance ratio.
We covered a lot of ground.
We did. We navigated terminal autoclave sterilization, endotoxin limits down to a quarter of a unit, and literally fought off E. coli in challenge testing.
It just means that the infrastructure, the science, and the sheer capital required to produce a genuinely safe biologic are monumental. The gap between a raw natural extract and a medical-grade therapeutic is a chasm of rigorous testing. Exactly. So whether you are sitting in a chair receiving a facial regenerative treatment to rebuild lost collagen, getting a joint injection to repair the cartilage in a bad knee, or even using specialized cell repair eye drops, those little acronyms, USP and EP, on a manufacturer's specification sheet are your invisible shields.
They really are.
They are the absolute only things guaranteeing that the DNA fragments are the precise molecular weight to activate your cellular receptors, pure enough to bypass your immune system without triggering an allergic reaction, and sterile enough to prevent a catastrophic infection.
They are the dividing line between legitimate medical science and modern-day snake oil. Without those compendial standards acting as the ultimate gatekeepers, you would just be injecting crude, dangerous biological waste.
It really makes you appreciate the invisible rulebooks keeping us alive, but, it also leaves us with a fascinating and highly provocative final thought for you to explore on your own.
Oh, what's that?
Well, right now, the global demand for these regenerative PDRN treatments is just exploding. It's revolutionizing both aesthetics and orthopedics. But that explosive demand is rapidly pushing the absolute limits of global salmon aquaculture.
Oh, absolutely. There's only so much naturally occurring DNA we can harvest from fish.
Which means the supply chain is inevitably going to hit a wall. So will we eventually see the industry shift toward synthesizing these exact specific nucleotide chains from scratch in a laboratory setting, completely eliminating the fish from the equation?
That would change everything.
And if we do achieve synthetic PDRN, how will the USP and the European Pharmacopoeia have to completely tear up and rewrite these incredibly dense rulebooks? How do you regulate and distinguish between a natural extraction and a synthetic creation when the molecules look absolutely identical under a microscope?
That is undoubtedly the next massive frontier of biological manufacturing. The rules of the game are going to have to evolve just as fast as the science itself.
It's a whole new landscape to watch out for. But until that synthetic future arrives, keep today's deep dive in mind. That clear liquid in the syringe isn't just medicine by default. It's the hard-won result of an incredibly complex, highly regulated, and deeply fascinating microscopic journey. Thanks for joining us as we unpack the invisible standards that make modern regeneration possible.